This video is an example of designing a bandpass filter. It is the second example from section 11.7.2 of Applied Analog Electronics. Let's take a look at what we're being asked to design. Alright, we're trying to do a bandpass filter, and this is a passive bandpass filter, so we're looking at a design that has just a voltage divider. This will be to Vref here. So, and this is called a CU and RU, and this CD and RD. Okay, we've got two corner frequencies. Where do we want to put them? Let's say 150 hertz and 20 kilohertz. And what is the peak gain that we want to try and get? Now, let's say we want to get it somewhere between 0.4 and 0.6 as the peak gain. We can't get a really high gain for a passive bandpass filter. We're always going to have some loss in it. So gain of a half sounds probably doable. If it turns out that's difficult to do, then you can relax the specs and compensate somewhere else in your overall design. But I think this one's doable. So let's take a look. Okay, so what do we need to do? First thing we need to do is to say, where is the peak gain going to happen? We say the peak gain is going to be around a half, but what frequency is that going to happen at? Well, we can take the geometric mean of our two corner frequencies to figure out where the peak gain is going to occur. So that's 150 hertz and 20 kilohertz. Multiply those together and we get 3 million. Take the square root, and what we've got is that this is going to happen at about 1.73 kilohertz. We can also look at this, however, by taking 2 pi times this, squaring it and inverting it to get the product of the two time constants. So multiply that by 2 pi, square it, and invert it, and we have RUCU times RDCD is going to be about 8.44 times 10 to the minus 9th, and that's in seconds squared. Alright, that's a constraint on sort of the overall time constant, just to get the center frequency about right. But now we want to do something where we set the overall gain to be about a half. And we had a formula for the gain of a passive bandpass filter like this, and it was RDCU divided by RDCU plus RDCD plus RUCU. So the two time constants in this sort of cross one, which is RD and CU. And that's going to have to be about 0.5. It's a little easier to solve this thing if we flip it upside down, because then we can do the division easily. So we would get RDCU over RDCU, that's 1, plus CD over CU, plus RU over RD is approximately 2. Alright, so this is, like many engineering problems, somewhat under-constrained. We have only 3 total constraints on our design here, what the two corner frequencies are and what the overall gain is, but we have 4 parameters. So at least one of the parameters we can adjust freely, just scaling everything. It's generally harder to get good capacitance values than to get good resistance values. They're more widely spaced in the components that are available usually. So one way we could try and do this is we could look at, try to make CD and CU being the same. That would give us a 1 plus 1, and if RU is very much less than RD, then we would have this as being about 2. So can we afford to do that? Can we make RU very much less than RD if the two capacitors are the same? And that depends largely on how far apart the corner frequencies are. If they're very close together, it's harder to make the design work. But if they're very far apart, then the two corners are almost independent of each other. They don't interfere, and you can probably make the resistance ratio quite large. And here we've got things that are 20 kilohertz to 150 hertz. That's more than 10 to 1, more than 100 to 1. That's a big difference. So I think we can get away with, let's make CD equals CU equals, we'll just call it C, and then we'll have to figure out what we want to use for that, and then we'll have to have RU a lot less than RD. Okay, so that's kind of removed one of our variables. We've now only got 3 variables to try and figure out, and we've got 3 constraints, so we probably could do it. And this set of things will get us the gain we want. So now all we have to do is try and figure out how do we get the corner frequencies. And for that, we have the lower corner frequency and the upper corner frequency to try and figure out. The lower corner frequency, we had that omega low was, I believe, 1 over, let's get the right pairing here, that's RDCU plus RDCD plus RUCU. So the same denominator here as we had up here. And we can figure out what omega low is, or we could just try flipping this thing upside down and get RDCU plus RDCD plus RUCU is approximately, we want that to be 1 over omega low, so 1 over 2 pi n times 150 hertz. All right, but we know that RU is a lot less than RD, and we know that the capacitors are all the same here. So what we've got is we've got RDC times C plus RD times C plus something a lot smaller than that. So we could just write this, working up the page here, as 2 RDC is about 1 over 2 pi times 150 hertz. All right, so what we had done here in doing that approximation is basically say this one we can get rid of because the RU is much less than RD. All right, this was now something we can do this calculation. 150 hertz, 2 multiplied by pi. Invert that. Oh, and we've got this 2 to divide out also. So we get RDC is approximately 530.5 microseconds. Okay, grab another sheet of paper here. So what have we got? We have RU is a lot less than RD. We've got CD equals CU. We've got RDC is about 530.5 microseconds. All right, now we've got to use the upper corner frequency, and the formula for the upper corner frequency was 1 over, and I've got to get the right pair here, RUCD plus 1 over RDCD plus 1 over RUCU, and that's going to be equal to 2 pi times 20 kilohertz, And 2 pi times 20 kilohertz, well, let's just figure out what that is. That's, that can't be right. Let me just try that again. 20 kilohertz, 2 times pi times, and that's 125.7 times 10 to the third. That's radians per second. All right. Can we simplify this thing? Again, all the C's are the same. So we've basically got 1 over RUC, 1 over RDC, 1 over RUC. Well, the RUCs are the same, so those can be added. So we have 2 over RUC plus 1 over RDC. But RU is very much less than RD, so 1 over RDC is much smaller than the 2 over RUC. We can probably just ignore that and say 2 over RUC is approximately the 125.7 E3 radians per second. We can invert that and multiply by 2 to get RUC is about 15.9 microseconds. All right, now if we look at the ratio of RDC and RUC, 530 over 15, that is, RD is very much larger than RU, so we're still meeting that constraint. We haven't cheated here. All right, now we need to just pick a value for C in order to get reasonable capacitor and resistor values and then check to make sure that all of our calculations are right. We want to have resistor values that are, say, between about 1K and 1 mega ohm. We can pick something like 10 nanofarads. All right, if we do 10 nanofarads, then RU is going to have to be this divided by 10 nanofarads. And that's about 1.59 kiloohms. So let's make it a standard value, 1.6 kiloohms. And RD would have to be the 530.5 nanoseconds. Do I still have that in here? Yeah. And that's, again, divided by 10 nanofarads. And that'd be about 53 kiloohms. Oh, 53 is not a standard value. 51 kiloohms is kind of close, though. All right, so here is a possible design. Now, we made some approximations here, picking up, rounding values and stuff like that. So we should check that it meets all of our constraints by going back through and plugging things in. And I often like to do that by actually doing a GNU plot of the gain as a function of frequency, and having GNU plot calculate the corner frequencies and calculate the peak gain for me. I won't bother working through that on this example, but if you do check it, you'll get the peak gain as being about 0.4923, I think, at 1762 hertz, which is close to that half. It's between the 0.4 and 0.6 that was our range that was acceptable. And the corner frequencies came out to be 153.6 hertz and 2206 hertz. And that's pretty close to what we wanted for the specs. You can obviously pick different values and get the same corner frequencies. For instance, if I decided I don't like these resistors being so small, I want larger resistors, I could multiply both of these resistors by a factor of 10 and take the capacitor down by a factor of 10. So I could have done 1 nanofarad, 16 kiloohms, and 510 kiloohms, and it still would have been reasonable values. I would have had exactly the same characteristics here. The difference would be that all the impedances are higher, so it puts less load on whatever's driving the input, but also it's more sensitive to any current being taken out of the filter. So if the filter wasn't directly driving an op amp or something else that didn't take any current, you might run into some trouble with the load changing the characteristics of the filter. So how big you want to make these resistors depends largely on how important it is that this not put any load on the preceding circuit versus how important it is that any load coming from the subsequent circuitry doesn't affect it. Okay, I think that's probably enough for this example.